In this video, we are going to use trigonometric substitution to evaluate an integral. Here's a question. Evaluate the integral of 1 over x squared square root of 9 minus x squared dx. And there are three major type of substitution we can make depending on what we have in the integral. In the integrand here we have square root of 9 minus x squared. So, and among the three, the first one is the most likely to be used because they are square root of a squared minus x squared. So in any case, we are going to use a triangle in order to see what is happening. So our substitution, recommended substitution suggests we use x equal a sine of theta. Now, a squared in this problem is 9. So we assume a is positive. So a in this case is a squared equals 9. That means a is 3. All right. So this is our theta. And the sine is equal to, so x equal 3 sine theta. It means that sine theta is equal to x over 3. So sine theta, which means opposite over hypotenuse. So x is here and 3 is there. Therefore, what we need to get now is the adjacent side. So we know that this is going to be square root of hypotenuse square, which is 9, minus opposite square, which is x squared. So with that we can answer the question. Now, doing this, dx is equal to 3. The derivative of sine is cosine theta d theta. And now going back to the integral, we have integral of 1 over x squared, square root of 9 minus x squared dx. Now remember, let's write this I so that we don't have to rewrite the integral all the time. We can just write I for integral. So theta. That is going to be, if we do this, sorry, this is x. Good. So replacing things with what they are, we said x is equal to 3 sine theta. So we square this, and then square root of 9 minus x squared is going to be what? So square root of 9 minus 3 sine squared, or theta, 3 sine theta squared. Alright, we do that. And then we have dx. And dx, we said it is 3 cosine theta d theta. Now we replace x squared with 3 sine theta square, and we replace wherever x is, we replace with 3 cosine sine theta. And this becomes 3 cosine theta divided by 9 sine square theta. Then now square root here will be of 9 minus 9 sine square theta, and we have the theta there. And continuing, we obtain, now note that if we take square root of a squared minus a squared sine theta, assuming that a is positive, sine squared theta inside, then that will give you square root of a squared 1 minus sine squared theta, and that should give you a absolute value of a, if we didn't know that a was positive, and 1 minus sine squared So a here is positive, so square root of a squared, square root of 1 minus sine squared theta, and square root of a squared is absolute value of a. In this case, a is positive, absolute value of a is a. And then 1 minus sine squared is cosine squared. Square root of cosine squared is absolute value of cosine. In this case, we are in the first, assuming that we are in the first quadrant, we just take cosine theta. Okay? So now using that here, it means that square root of 9 minus 9 sine squared would be just 3 cosine theta. So this said, our integral will become 3 cosine theta divided by 9 sine squared theta times 3 cosine theta, and all this the theta. So I will see that we do have 3 and 3. We also have cosine theta and cosine theta. So in each case, we get one left as the result of simplifying. Okay, so, and the integral becomes then 1, we can 1 over 9 k sine squared theta d theta. And using this, that is 1 over 9 integral of cosecant squared theta d theta. And this is negative 1 over 9 k cotangent k theta plus constant, because the derivative of cotangent theta is negative cosecant squared theta. So this said, now because since we have this triangle, we come here, we can see that cotangent theta is adjacent over hypotenuse. That means square root of 9 minus x squared over, adjacent over opposite over x. And using this, in the integral, we conclude that integral of 1 over x squared square root of 9 minus x squared dx is negative 1 over 9, okay, square root of 9 minus x squared divided by x plus constant. And that's the answer.